Okay, let's unpack this. Seeing the invisible, I mean, that's the stuff of comic books and sci-fi movies, right?
Totally.
Except now it feels like we're stepping right into that world with all the buzz around these supervision contact lenses.
It really does.
It makes you think, how limited our regular eyesight actually is. We're stuck in that tiny, tiny slice of the electromagnetic spectrum, like 400 to 700 nanometers.
It's a sliver.
And these lenses, they're aiming for the near infrared, that 800 to 1600 nanometer range. It's a whole other world of light out there.
And this isn't just some pie-in-the-sky idea. This is coming from serious researchers, right?
Yep.
University of Science and Technology of China.
Exactly. USTC. Their work's published in Cell, a top journal. And you can find popular science articles breaking it down, too. It just taps into that fundamental human curiosity, doesn't it? To see beyond our natural limits.
Well, yeah, and think about how we've tried to do this before. Night vision goggles.
Right.
They get the job done, sort of. But they're clunky. They need batteries.
Oh, yeah. Heavy.
You're looking at that weird green world through a toilet paper tube view.
Yeah.
And you can't see normal visible light at the same time.
Exactly. You're lugging all this gear around, but these contact lenses, the promise is just, wow, it's on another level.
Mm-hmm.
Power-free, non-invasive, you just pop them in, and suddenly your eyes are supposedly taking in near-infrared light and converting it directly into visible light right there on the surface.
It's this seamless integrated vision they're talking about.
Yeah.
A completely different paradigm.
Yeah.
And if we boil it down to the core science, this almost magical ability translating invisible light into visible, and it all comes down to these incredibly engineered materials, nanoscale stuff, up conversion nanoparticles, or UCNP.
The UCMPs.
They're the absolute key.
Right, the UCMPs. So how did these tiny, tiny particles actually manage this trick, turning one kind of light into something completely different?
Okay, so at its heart, it's a type of physics called a nonlinear optical process. Specifically, up conversion. It's a kind of luminescence, actually. Think glow sticks. Yeah. But way more complex. Here, the UCMPs absorb multiple lower energy photons, those near-infrared ones we can't see. And then it's almost like they bundle that energy together.
Like collecting small change for a bigger bill.
Exactly like that. They absorb several NIR photons and then emit one single photon that has higher energy, high enough that we perceive it as visible light. Sometimes it's called anti-Stokes luminescence.
Okay. So it's not just a simple one-for-one swap, invisible in, visible out?
Nope, definitely not. And the way it happens is, well, pretty elegant, really. It's sequential absorption. Think of it like climbing an energy staircase.
Okay.
The nanoparticle absorbs one NIR photon, gets boosted to a temporary sort of stable energy level a step. Then it absorbs another NIR photon, gets boosted higher.
Another step up.
Right, until it reaches a high enough energy level that it can finally relax back down by emitting that single higher energy visible light photon.
And these steps are, what did you call them?
Metastable intermediate electronic states. Basically temporary parking spots for the energy. And this whole step-by-step climbing process is really characteristic of certain elements, the trivalent lanthanide ions.
Lanthanides, like elements from the bottom of the periodic table.
Exactly. Things like erbium, ytterbium, their unique electron structure, these shielded 4f electrons and lots of available energy levels, makes them perfect for this multi-step energy ladder.
Gotcha. So the lanthanides are the real workhorses doing this invisible to visible conversion. How does that energy actually get handed off inside the UCMP? You mentioned climbing steps.
Right, so there are a few physics mechanisms, but for these lenses, the most probable, the dominant one, is likely something called energy transfer up conversion, or ETU.
ETU?
Think of it as teamwork. You deliberately put two types of lanthanide ions into the nanoparticle, sensitizers and activators.
Sensitizers and activators.
Yeah, the sensitizers act like really good antennas. They're great at grabbing those passing NIR photons. Then they hand off that captured energy to nearby activator ions.
Okay, like a relay race.
Kind of. And these activator ions collect energy from multiple sensitizers, or even internally transfer energy, climbing those steps until they have enough juice to make the big jump, emitting the visible light.
Interesting. Are there other ways it can happen?
Oh yeah, there are other cool mechanisms like excited state absorption, ESA, photon avalanche, PA, cooperative sensitization. But for these contact lenses, ETU, with that sensitizer activator team, is really the prime suspect for how they're pulling off this trick.
Okay, so we've got these UCMPs, these nanoparticles, and inside they're packed with these two types of lanthanide ions working together. Let's zoom in a bit. Who's doing what?
Right, so Yeah, within each UCNP, you basically have three crucial components working together: the host matrix, the sensitizer ions, and the activator ions.
Okay, let's start with the sensitizers, the antennas, right? Who are the key players grabbing that NIR light?
Ytterbium, Weibu. It's a very common
Yeah.
and really efficient sensitizer. And yeah, it's confirmed to be used in these lenses.
Ytterbium. Okay.
Think of it as the main solar panel for the UCNP. It's particularly good at absorbing NIR photons right around 980 nanometers.
A specific wavelength.
Yeah. Once it absorbs a photon, it gets excited, and then very efficiently transfers that energy packet over to the activator ions nearby. But the concentration matters.
How much you put in?
Exactly. Not enough ytterbium. You don't capture enough NIR. Too
Mhm.
much. And you can actually start losing energy in ways you don't want. It's a balancing act.
And the activators, they're the ones taking that harvested energy and actually making the light we see.
Precisely. Erbium, Uricu, and thulium are common choices. They have these more complicated energy level structures that let them accept energy in those sequential steps we talked about.
Right, the staircase.
And eventually, they emit visible light.
Mm.
Erbium, like the one used in these lenses, tends to give off green and sometimes red light. Thulium can produce blue light, and interestingly, also some NIR light around 800 millimeter.
So the scientists can basically tune the color by picking the right activator.
And the right combination and concentrations. It's all about engineering the mix to get the specific visible colors you want emitted when the NIR hits them.
Okay, so you've got these tiny ions doing complex quantum physics. They must need a stable place to live, right? That's the host matrix job.
Exactly. The host matrix is the crystal structure, the house, that holds and supports these lanthanide ions within the nanoparticle.
What makes a good host?
Ideally, you want a material with low phonon energy. Photons are like vibrations in the crystal lattice.
Okay.
If you have too many energetic vibrations,
Mhm.
they can basically steal the energy from the excited lanthanide ions before they emit light and release it as heat instead. That's bad for efficiency.
You want light, not heat.
Right. So low phonon energy minimizes that loss. The host also needs to be chemically stable. You don't want it falling apart in your eye. It needs to be biocompatible, obviously. And its crystal structure needs to have the right kind of parking spots, crystallographic sites,
Okay.
for the sensitizer and activator ions to sit in comfortably.
And what are they using here?
Sodium, gadolinium fluoride, NaGDFA. It's known to be a very efficient host, especially in its hexagonal crystal phase, the beta phase.
Gadolinium. That name rings a bell. Medically speaking. Aren't there some concerns about gadolinium sometimes?
That's a really important point to bring up. Yeah, you're probably thinking of gadolinium-based contrast agents used in MRIs.
Mhm.
There have been concerns about gadolinium potentially sticking around in the body with some of those agents.
Right.
Now, in this NetGDF structure, the gadolinium ions are locked within a more stable crystal lattice. However,
But
for something like a contact lens, sitting directly on the eye for potentially hours a day, day after day, the question of long-term stability is crucial. Could any gadolinium ions leach out over time in the tear film environment? That absolutely needs very careful, thorough investigation.
okay, good to know. Now, I saw something, one of the popular articles mentioned gold nanoparticles being part of this, but you're saying the main USTC research doesn't list gold for these 2025 lenses.
That's right. There seems to be a bit of a disconnect there between some popular reports and the core scientific papers on this specific iteration of the lens.
So what can gold nanoparticles do with UCMPs? Is there a reason they might be mentioned?
Well, yeah, gold nanoparticles can interact with UCMPs in fascinating ways. Sometimes they cause plasmonic enhancement.
Plasmonic enhancement.
Yeah, it's a physics thing where the gold can basically amplify the light nearby, potentially boosting either the absorption of the NIR light by the UCNP or the emission of the visible light from the UCNP.
That sounds useful.
It can be. But gold can also sometimes do the opposite quenching, where it actually reduces the light emission. And getting that enhancement effect requires incredibly precise engineering. You need the exact right size, shape, and spacing of the gold relative to the UCNP.
Tricky.
Very. So given that gold isn't mentioned in the primary research for these specific lenses, it's highly probable that's not actually part of their current design. Maybe something explored earlier or for other applications, but likely not in these ones aiming for 2025.
Okay, so probably no gold. But what about these core shell structures I've read about with nanoparticles? Are those important for how these UCMPs work in the lenses?
Oh, absolutely crucial. Core shell architectures are key for squeezing out as much efficiency or quantum yield as possible from the UCNPs.
Quantum yield meaning how much visible light you get out for the NIR light that goes in.
Exactly. Think of it like a fancy gobstopper. You have the core, where the main upconversion action happens. That's where your sensitizers and activators are doing their thing.
Okay.
Then you add a shell, an outer layer. This shell serves a couple of purposes. An inert shell, often made of something similar to the host matrix, but without the active ions, like sodium, deuterium fluoride, or even more NaGDOFU. Its main job is to protect the core.
Protect it from what?
From surface defects. See, the surface of any nanoparticle is a messy place, electronically speaking. These defects can act like traps, grabbing the energy before it can become light. We call it surface quenching. The shell smooths over those defects, like putting a protective coating on something. This is especially vital for tiny nanoparticles where a lot of the atoms are near the surface.
Makes sense. Any other kinds of shells?
Yep. You can get even fancier with active shells. You can strategically place different sensitizers or activators in different layers, maybe sensitizers in the core and activators in the shell, or vice versa, to really optimize how the energy flows. Or you can even build up multiple shells to enable really complex functions, like getting different colors out for the trichromatic vision we might talk about later.
So even if the papers on these specific lenses don't spell out core shell, you think it's almost certain they're using them?
Given the team's prior work, their 2019 Cell paper on injectable nanoantenna used really sophisticated core at shell structures, and just the fundamental physics challenge of getting UCMPs bright enough to see under low NIR power. Yeah, it's an extremely educated guess. It's highly probable they're using core shell engineering.
Right.
Plus, when they talk about modifying the surface of the UCMPs to mix them into the contact lens polymer, you usually do that after making the core shell nanoparticle. Getting enough efficiency, enough brightness is the challenge. Core shell is how you tackle that.
All right, so we've got these super optimized, likely core shell UCMPs. Now the next big step, how do you actually get them into a contact lens, something someone can comfortably wear? What are the material science hurdles there?
Okay, yes, several big ones. First, the lens material itself. They're using poly-2-hydroxyethyl methacrylate, FEMA.
FEMA, that sounds familiar for contacts.
It is. It's a very common, well-established, soft contact lens material. It's generally biocompatible, transparent, and has the right kind of flexibility and water content.
So that's a good starting point. What's next?
A huge challenge is matching the refractive index. That's basically how much the material bends light.
Okay.
If the UCMPs bend light differently than the FEMA polymer surrounding them, the light scatters everywhere. The lens looks cloudy, hazy, useless for seeing through.
Right, you need it to be clear.
Absolutely.
Yeah.
So the USTC team found a specific formulation, they call it FEMA-1, that has a refractive index very similar to their UCMPs after they've been treated to be compatible with the polymer. They call them oleate-free UCMPs. This close match allowed them to get over 90% transparency in the visible spectrum, even with the nanoparticles mixed in.
That's impressive. But you need enough nanoparticles in there to actually do the light conversion, right? How do you load them in without messing up that transparency or making the lens weak?
Exactly. It's a trade-off. You need sufficient loading enough UCMPs by weight to generate a visible signal you can perceive. They reported successfully getting about 7 to 9% UCMPs by mass into the FEMA-1.
And it was still clear.
Remarkably so. Still 85 to 90% transparent in the visible range, they said, and with good optical performance overall. But getting them dispersed evenly is critical.
No clumps.
No clumps. If the nanoparticles aggregate, you get opaque spots, and it can also create weak points in the lens structure. And remember how nanoparticles are often made with oily hydrophobic coatings like oleic acid?
Yeah.
Well, FEMA is hydrophilic. It likes water. So you have to modify the UCMP surface. You either swap out those oily ligands or coat the nanoparticles with something water-friendly, like a thin layer of silica or maybe peg chains. This makes them happy to disperse evenly in the FEMA mixture and also helps with biocompatibility.
Okay, so surface modification is key. How do they actually embed them then? Mix them in like cookie dough?
Sort of.
Yeah.
A common method is to disperse the surface-modified UCMPs really well into the liquid hemomonomer, the basic building block molecule, before you polymerize it.
Before it turns solid.
Right. Then, as the hemomolecules link together to form the solid FEMA polymer network, the nanoparticles get physically trapped within that structure, hopefully evenly distributed. The USTC team calls their product UCNP's fused FEMA-1 UCLs, which suggests this kind of integration.
And does adding these nanoparticles affect the lens properties much? Like its strength or feel?
Studies on similar UCNP-doped materials generally show that if you do it right, good dispersion, compatible surfaces, it doesn't significantly harm the mechanical properties, the optical quality, or the surface characteristics. And initial biocompatibility tests look good too.
And comfort is huge for contacts. They need to stay wet, right?
Absolutely crucial. Hydrophilicity, loving water, and wettability, letting the tear film spread smoothly, are vital for comfort and keeping the eye healthy. The researchers reported their UCNP lenses showed satisfactory optical performance, hydrophilicity, and biocompatibility in their early tests.
Okay, so imagine the lens is in, it's comfy, it's clear. How does it actually let you see the near-infrared light? Walk me through that perception process.
Okay, so the UCNPs scattered throughout the contact lens material are just sitting there. When near-infrared light in that target range, say 800 to 1600 millimeter, hit the lens, those UCNPs absorb it. They do their upconversion magic, turning that low-energy NIR into higher-energy visible light, maybe green light, if they used erbium activators.
So the nanoparticle itself starts glowing green?
Essentially, yes. It emits visible light right from where it sits inside the lens material. That visible light then travels out of the lens, enters your eye through the pupil, just like normal light, and hits your retina.
And stimulates the rods and cones.
Exactly. Your normal visual system picks it up.
So wait, is the lens projecting like a sharp NIR image onto my retina, or is it different?
That's a really interesting point. It's different. The spatial information from the original NIR source gets a bit diffused because the light emission is happening from the UCNPs spread within the lens material itself.
Oh, okay.
So basically, any part of the lens that gets hit by NIR light will appear to glow. Your eye then forms an image of that glowing pattern on the lens.
So I'm seeing the lens glow, not the original NIR object sharply.
Pretty much. That glowing pattern is superimposed on whatever you're seeing normally in the visible spectrum. This means the spatial resolution, the sharpness of the NIR information you perceive just from the lens, isn't going to be super high. It's more like seeing a blurry glow indicating where the NIR source is.
Okay, that makes sense. It explains that coarse perception they mentioned. Now, what about this weird eyes closed thing? Seeing flickering NIR better with eyes shut. That sounds totally backwards.
It does sound counterintuitive, right?
Yeah.
But there are a couple of good reasons. First, NIR light is actually much better at penetrating through biological tissues, including your eyelids, than visible light is.
Really? Okay.
So a decent amount of the NIR signal still reaches the contact lens, even with your eyes closed. Second, and maybe more importantly, closing your eyes blocks out almost all the ambient visible light.
Less background noise.
Exactly. The faint visible light being generated by the UCNPs isn't competing with bright room light or sunlight anymore. It's like trying to hear a whisper in a quiet room versus a noisy party. The signal-to-noise ratio dramatically improves.
So you can pick up weaker or flickering signals more easily?
Precisely, like that flickering NIR Morse code they demonstrated.
That's actually really clever how that works out. Now they're even talking about achieving NIR color vision with these trichromatic UCLs. How on earth do you see colors in light that's invisible?
Yeah, this is where the nanoparticle engineering gets seriously sophisticated.
Yeah.
Trichromatic upconversion contact lenses, or TUCLs.
Ah.
The goal is to make different wavelengths of NIR light appear as different colors to you.
Wow.
By designing the UCNPs very carefully, probably using those complex core multi-shell structures we talked about, they dope different nanoparticles or maybe different layers within a nanoparticle with specific combinations of lanthanide ions. These combinations create distinct pathways for energy absorption and light emission, depending on the exact wavelength of the incoming NIR. So, for example, they might engineer one type of UCNP that absorbs NIR around 808 millimeters and glows green. Another type might absorb 980 millimeter NIR and glow blue. And maybe a third type absorbs 1432 millimeter NIR and glows red.
So you need different sensitizers for different NIR wavelengths?
Probably. Maybe neodymium, NDR, which is good around 808 millimeter, coupled with erbium for green. Then ytterbium, which likes 980 millimeter, maybe coupled with thulium for blue. And maybe erbium again, perhaps in a different host or configuration, for red emission from 832 millimeter excitation. It gets complex.
So you could potentially distinguish between 3 different flavors of NIR as blue, green, and red.
That's the idea. It opens up the possibility of not just seeing NIR, but actually differentiating between NIR sources based on their wavelength signatures. It's a huge leap.
And could this also help with regular color blindness?
That's another fascinating potential application. If you could design UCNPs to absorb visible wavelengths that someone struggles to differentiate like certain reds and greens, and then re-emit that energy as a different visible color they can easily distinguish. Yeah, it could potentially help correct certain types of color vision deficiency.
That would be amazing. But developing these TUCLs sounds incredibly challenging.
Oh, absolutely. The material science and engineering required are definitely non-trivial.
Okay, so let's talk performance metrics. You said the lenses alone give coarse resolution. Could I read an eye chart in a dark room with just the lenses?
Unlikely, based on the current descriptions. Just the lenses give you that sort of glowing indication of where the NIR is. To get sharpness resolution comparable to normal vision, they developed that supplementary eyeglass system.
Right, the glasses that go with the contact.
Yeah. It seems the glasses have some kind of optics, maybe lenses or filters, designed specifically to take the somewhat scattered visible light coming off the contact lens and focus it properly, creating a much sharper image of the original NIR scene. They call it optimized optical imaging.
So it's a two-part system for high-detail NIR vision right now.
That appears to be the case for achieving high fidelity.
Okay. What about sensitivity? How faint an NIR source can these detect? Could I use them for passive night vision? Just seeing ambient NIR?
That's the million-dollar question, really. Right now, the demonstrations seem to use active NIR sources, like infrared LEDs shining light.
Meaning they need a fairly strong signal.
It suggests there's a threshold, yeah. A certain amount of NIR photons need to hit the UCNPs to generate enough visible light for you to notice. A huge goal for the research is definitely to boost that sensitivity way up.
To see things like natural night glow or thermal heat.
Exactly. To achieve true passive night vision, where you don't need an IR flashlight, they need to make those UCNPs much, much more efficient at converting those very faint ambient NIR photons. Improving that quantum yield is key.
But they could detect flickering light, right? The Morse code example.
Absolutely. Humans wearing the UCLs could accurately perceive and decode simple flickering NIR patterns. And in earlier mouse studies with the injectable version, the mice could even tell the difference between different frequencies of flickering NIR.
Which suggests potential for covert communication.
Potentially, yes.
Yes.
Using NIR signals that are totally invisible to anyone without the special lenses.
And the field of view, is it like looking through binoculars?
They don't give exact numbers, but the implication is that because it's a contact lens covering your cornea, the enhanced vision would likely cover a wide natural field of view, much better than the tunnel vision you often get with goggles. That's a potential big ergonomic plus.
Okay, and we touched on NIR color with TUCLs and potentially helping visible color blindness. And the kicker, no batteries.
0 batteries? That's a massive advantage, totally passive operation. The energy comes entirely from the incoming NIR light itself. That really simplifies the design compared to, say, smart contact lenses that need power.
Now, this USCC team, this isn't their first rodeo with this kind of tech, is it? I remember hearing about something injectable a few years back.
You're absolutely right. That was their big 2019 paper in Cell. A different approach, but definitely related. They developed injectable nanoparticles, PBUCNPs, photoreceptor binding, upconversion nanoparticles.
So photoreceptor binding, so they stuck to the cells in the retina.
Exactly. You'd inject them into the eye, and they were designed to anchor themselves directly onto the surface of your photoreceptor cells, your rods and cones.
Whoa, so the light conversion wasn't happening in a lens on the front, but right at the light detectors?
Precisely. The PBUCNPs absorbed incoming NIR and emitted visible light directly onto the light-sensitive proteins, opsins, within the photoreceptors, essentially stimulating them as if they'd seen visible light. It made the retina itself sensitive to NIR.
What were those nanoparticles made of? Similar stuff.
Yeah, similar core ideas, lanthanide dopants like ytterbium and erbium, but in a sodium yttrium fluoride, NIOARIS, host matrix that time, I believe. And they definitely had some specific surface chemistry to make them stick to the photoreceptors.
And did it work?
In mice, yes. Remarkably well. The mice could perceive NIR light, even distinguish NIR patterns alongside their normal vision. And apparently with negligible side effects reported at the time. It was a huge proof of concept for extending vision.
So if the injections work so well, why switch to contact lenses? Seems less direct.
Invasive versus non-invasive, that's the main driver. Injecting things into the retina. It's a complex procedure, carries risks. It's just not practical for widespread use in humans.
Right. Much higher barrier.
Exactly. The contact lens approach, while it has its own engineering challenges like getting the UCNPs into the lens material effectively, is vastly less invasive, much more feasible for real-world applications, so it was a strategic shift.
Moving the conversion from the retina to the lens surface.
Right. The visible light is generated in the lens, and then your eye just sees that visible light normally. This shift required those big leaps in material science, getting high UCMP loading, maintaining transparency, ensuring biocompatibility of the FEMA lens. And now they've moved to human trials, showing NIR perception and even hinting at that trichromatic potential.
Which brings us back to safety. Anything going in or on your eye needs to be incredibly safe. What are the big safety questions here?
Absolute paramount. Okay, first, the lens material itself. FEMA has a long track record, generally good biocompatibility, good water content, but any long-term contact lens wear can have issues, protein deposits, lipid buildup, potential for microbial contamination since FEMA isn't inherently antimicrobial.
Standard contact lens issues.
Right. The USTC team reported satisfactory biocompatibility in their initial UCL tests, but you absolutely need thorough, long-term clinical studies to see how these UCNP-loaded lenses behave over months or years of wear.
And the nanoparticles themselves, the lanthanides, the gadolinium host, potential toxicity?
That's the really critical area needing more data.
Yeah.
Generally, UCMPs are thought to have fairly low acute toxicity because the active ions are locked inside the crystal structure.
But long-term exposure is different.
Exactly. We need to know if any of those ions, especially the lanthanides, and especially gadolinium, given its history, could potentially leach out slowly over time when exposed to tear fluid on the eye surface. What effect would those free ions have?
Even if the NADGDF Euro lattice is stable, is it stable enough for decades of exposure?
That's the question. How stable is that lattice long-term in the biological environment of the terafilm? We just don't have enough data yet on the chronic ocular effects of this specific type of nanoparticle exposure. And if they ever did add gold back in.
Then you'd worry about gold toxicity too.
And potentially photothermal effects. Gold nanoparticles can heat up when they absorb light, which might not be great on the eye. Plus, gold nanoparticle toxicity can depend heavily on size, shape, and coating. But again, probably not relevant for these lenses.
So even though it's non-invasive compared to injection, the long-term presence of these nanoparticles on the eye surface needs careful scrutiny.
Definitely. Beyond chemical leaching, you have to consider potential mechanical irritation. How do the nanoparticles interact with corneal cells, conjunctival cells? Could they get absorbed, transported elsewhere in the eye, or even systemically over long periods? What's the ultimate fate of these UCMPs? Do they stay locked in the FEMA forever? Does the FEMA degrade? These are all open questions needing answers from long-term studies. The safety profile is just fundamentally different from the injectable ones, and it's new territory.
Okay. So assuming the safety hurdles are cleared, what's the bigger picture? Beyond night vision, what could this tech be used for?
Oh, lots of potential avenues. We've mentioned correcting color blindness, secure communication via invisible NIR signals, maybe enhancing vision in fog or dust where NIR penetrates better. You can imagine anti-counterfeiting applications embedding unique UCNP signatures in products. Medical diagnostics may be detecting specific biological markers that absorb or emit NIR. Even search and rescue spotting heat signatures or specific NIR beacons.
How does this stack up against all the hype around augmented reality, AR contact lenses, or smart lenses? Are they competitors or different things?
They're really quite different beasts, fundamentally. These USTC lenses are about sensory augmentation, making the invisible visible. And crucially, they're passive, power-free.
Right.
AR smart lenses from companies like Mojo Vision, InWith, maybe Samsung, they're focused on information display, projecting digital info onto your view. Or maybe biosensing. They need active electronics, micro displays, power sources, data connections.
So USTC is changing the input signal. AR is overlaying digital data. Exactly. Different goals, different technologies. They'll both push the boundaries of what a contact lens can be.
What are the biggest challenges ahead for these NIR lenses? What needs to happen next?
Several key things. Improving that standalone spatial resolution, making the view sharper without needing the glasses would be huge. Dramatically enhancing the sensitivity for passive detection of low-level ambient NIR. That's critical for real-world night vision. Getting that comprehensive long-term safety and biocompatibility data through rigorous human trials, that's non-negotiable.
Absolutely.
Expanding the spectral range, maybe detecting more NIR wavelengths, producing a wider palette of NIR colors, and then the practical stuff. Scaling up manufacturing, reducing costs, ensuring durability and comfort for long-term wear.
It sounds like a massive interdisciplinary effort.
Totally. Materials, science, photonics, optics, ophthalmology, toxicology, they all have to work together.
So pulling it all together, these supervision lenses, they feel like a really significant step, don't they? Taking sci-fi towards reality. Absolutely. The core idea is non-invasive NIR perception, totally power-free operation, the potential for NIR color vision. They're genuinely remarkable innovations. And watching the scientific journey from those injectable particles to these human-tested lenses, it shows real dedication and cleverness.
What should we, the listeners, be watching for next? What are the key milestones?
Definitely watch for improvements in resolution and sensitivity. Those are the big performance metrics. Keep a close eye out for any published long-term safety data. That will be critical for acceptance.
Right.
And look for demonstrations moving beyond the lab into more realistic scenarios. How well do they actually work in the real world? Also, it'll be fascinating to see how this passive sensory tech evolves alongside the active AirSmart lens space. Do they stay separate paths, or do they start to converge somehow?
You know, just stepping back, the whole concept, there's a huge nerd out factor here, isn't there?
Oh, I would definitely.
Manipulating light at the nanoscale, embedding these tiny light-converting engines into something as ordinary as a contact lens, and the result is you can literally see a part of the spectrum humans aren't supposed to see.
Yeah, and that eyes closed phenomenon is just wild. Perceiving invisible light better when you block visible light.
And the idea of NIR colors, seeing distinctions in the invisible, and it all works without batteries. It's just elegant. It feels so clean.
It really does. Extending a fundamental human sense like vision, it's just a testament to scientific ingenuity.
Yeah, it's clearly groundbreaking and a very different path than AR overlays. But like you said, those performance and safety hurdles are still pretty significant before this becomes an everyday reality.
For sure. Cautious optimism is probably the right attitude.
It really makes you wonder, though, how else might nanotechnology allow us to subtly, maybe even seamlessly, expand what our senses can perceive? It suggests maybe even our most fundamental senses aren't quite as fixed as we usually assume.